of quantum computing as well as structure of the quantum computing. Here, the next session we have it as a mathematical foundation of quantum mechanics in computing. So here we have a lot of mathematical part we have. So we'll discuss some of the mathematical terms and some of the algorithms we discussed today. So definition of this one, the mathematical foundation of quantum mechanics in computing is the framework of mathematical tools, primarily linear algebra, complex vector spaces, probability theory, and operator theory. That is used to describe the behavior of quantum system, model quantum states, and it performs that computations on quantum computers. That is the definition. So how the linear algebra, how the complex vector spaces and probability theory and all, how we are using in that quantum computing, we'll discuss that. In this mathematical foundations, in this mathematics, behind that qubits, quantum gates, measurements, and algorithms is there. We'll see some of the example for qubits and quantum gates and measurements and algorithms. We'll discuss with example. And first slide is showing that operations on qubits. I think everybody knows about that, how the qubits, what is the state of the qubits, like that. So this slide shows about that operations on qubits, that mainly it's a reversible logic. So what is that reversible logic? See here, due to nature of quantum physics, the destruction of information in the gate will cause heat to be evolved when can destroy the superposition of the qubits. How the heat given after that, how the stopped after the heat, how it will be go for the previous state. So that is a thing here, same. The destruction of information in a gate will cause heat to be evolved, which can destroy the superposition of the qubits. Example of this, suppose you take that AND gate. So how is that? Two input AND gate, and we have that one output. So what are the inputs is there? A, B. C is an output. Two inputs A and B. So the state of 0, 0, the output is 0. And you know very well about that gate and all. 0, 1, the AND gate is output of this 0. And 1, 0, the output is 0. 1, 1, we have that output is 1. So in this case, three cases, information is being destroyed. And we can get only the value is 1, 1, we can get 1. The type of gate cannot be used, this type of gate cannot be used. So what type of gate we are using? Non-gate, like that. We'll see in the next slide. We must use that quantum gates. So what are the quantum gates are there? See this, quantum gates. So what is quantum gates? Quantum gates are similar to classical gates, but do not have a generate output. Their original input state can be derived from their output state uniquely. After that, they must be reversible. This is the important of this one. So what is that quantum gates? Quantum gates are similar to classical gates only. I previously, last session also, I told about that the output must be remain same in the classical computing, but when we go for that quantum computing, the output is not the same. That's why we have a probability of that. So here same, we have information about that. The quantum gates are similar to classical gates, but do not have a generate output. The original input state can be derived from their output state uniquely. They must be reversible. And this means the deterministic computation can be performed on a computer, quantum computers, only if it is reversible. So we can get the output based on that it's reversible only. Luckily, it has been shown that any deterministic computation can be made reversible. So I think you understand what is quantum gate. See this, various quantum gates we have that. What are the quantum gates? Analogous to classical logic gates, quantum gates manipulate qubits to perform operations like superposition, entanglement, and measurement. So already we discussed about that, what is superposition, entanglement, and measurement. To contrary of this, many conventional logic gates and quantum gates are reversible. See that what are the gates are available. See operator Pauli of x, that is gate is x. nor that what is the output of this is matrix of 0 1 1 0, and Pauli of y, that is a y is operator. What is the gate is used for this? See that symbol is there of y, gate of y. So what is the output? 0 minus 1 and 1 0, like that. If you go for same like that, Pauli of z, so gate of z, the matrix is 1 0 0 of minus 1, and header mod h is one of the important concept we have in this quantum gates. It represents as a h head mod. So what is the matrix for this head mod? That is 1 by root of 2 into 1 1 1 minus 1, and face of s comma p, s gate, and 1 0 0 in. Like that we have a pi of 8t and a controlled not CNOT. There is a C naught, there is a C of X, CX. See that gate, how it's represented, that controlled not gate. So I think you see that symbol of this one. So that one we are using in example. So what is the representation of matrix is 1 0 0 0. So same like the 0 1 0 0 0 0 0 1 0 0 1 0, like that, and controlled edge, that is CZ. So what is the gate state, how it will be represented, and what is the output of matrix? Swap, the same control, the controlled not C naught value will be swap. So how you can swap that? So this is a one more gate, swap gate. So how the matrix will be represented? So in that swap gate, second row and third row will be swapped. Next. So these all are the gates we have that. So actually we already mostly about that classical logic gates. Same like that we have a quantum gates. So example of that quantum gates. See that if you give input, so ket of psi equal to alpha of 0, ket of 0 plus alpha 1 of ket of 1. So this is the input we are giving. So two states we are having that input, that is 0 and 1. So if you give that input, there is one qubit gate. So what is the output? In that one gate, we are represent that G11, G12, G21, G22. So it will be the output. So once the input is given to one qubit gate, so output of this is, so ket of pi equal to alpha of 0 dash of 0 state plus alpha 1 of 1 dash of 1 get 1. So this the adding of these two state we can get is an output, that is alpha 0 of dash, alpha 1 of 1 dash, alpha 1 dash, alpha 0 dash. And same thing we can represent in this form. I already told about that output alpha 0 dash and alpha 1 dash, that is equal to G11, G12, G21, G22 into alpha 0, alpha 1. So this is the output we can get it from that one qubit gate. See here, that is first symbol is gate, that will identify that gate, that is leaves a qubit unchanged. And second one, X or not gate, it transposes the components of an input qubit, that is XOR not gate, transposes the components of an input qubit. And Y gate, Z gate, flips the sign of a qubit. We can see example how the sign will be flips. So Z gate is user flips the sign of a qubit, and H, the Hadamard gate. So these gate symbols already we see in the previous slide, and what is the output of the matrix format, like that. And quantum gates for Hadamard. So what is that Hadamard one? This is the simplest gate, involves one qubit, and it is called a Hadamard gate. Also we can call it as a square root of NOT gate. So we can represent this gate. See this diagram. The state of this first state, we are giving one input into one Hadamard and another input in the right hand side of state of 1. In between, we have a combination of these two states. Between two Hedmer gates, we can have a state of 0 plus of 1. So two Hedmer gates used in succession can be used as a NOT gate. Okay, here there is a point. Hedmer gate can used for as a NOT gate. That is one type of gate, Hedmer. And another one, if you go for this quantum gates, called as a controlled NOT. So what is that? Controlled NOT, you can tell it as a CN gate. A gate which operates 2 qubits is called a controlled NOT CN gate. Here we have two inputs. See this one, the bit of that one is control line. The bit on the control line is 1. Invert the bit on the target line. Previously, I told about that, flips the signal, flips the input. That is the thing. Here we have here. The bit on the control line is 1. It will invert the bit on the target line. See the diagram, we have two lines. One is a target line. A is the target line, B is the control. So if you A go for CN gate, that is controlled NOT. The output is A dash. For this support, we have a B control. The B control not having any changes, the same output we can get it. What we have it in the B control, the same we can have as a B not. So the B dash. So only we can get it the variation in A dash because of the controlled NOT gate. The controlled NOT gate is effect with the B control. The A target can be affected by the B control. See the example of this input. We have an input and output A, B. The output we have a dash, B dash. See that A 0, 0. The output of A is 0 and B is 0 because there is no any presence of control, B control. Understand that? Then if you go for second input 0, 1. So A value is 0, but B value is 1. So I already told that if the control value is 1, it will invert the bit on the target line. So the A value will be inverted. So we can get the output as a dash is 1. So we can get the value is 1, 1. And if you go for the third one, A value is 1, but B value is 0 only. So B value is 0 means there is no any invert bit. So again, the input value is 1. The output also the remains same, 1, 0. Then if you go for the last one, input is 1, but B input is 1. We already discussed that the bit on the control line is 1 means the invert the bit on the target line. So now B value is 1. So the invert the input of the A. So input of the A is 1. So it will be inverted and we can get the output as 0. That's why the last line A dash, that is A dash is we can get the 0 and B dash is 1. So this is the way of getting the output in this quantum gates controlled NOT. So we have two lines. One is a target line, another one is a B control line. A target line can be controlled by the B control based on the value. The bit on the control line is 1. It will invert the bit on the target line. Understand that? You able to follow?
Yes, sir. Yes, sir.
Okay. Then if you go over the next slide, that operation multiplication by 2. So we can build a reversible logic circuit to calculate the multiplication by 2 using CN gates. So arranged in the following manner. So input is carry bit, ones bit. Output is carry bit and ones bit. So 0, 0. So there is no any carry. Then we get the values also, output also 0, 0. And 0, 1. If you have that value bit 1 bits, there is a carry is there 1 and 1 bit is 0. So this is a simple way we can represent that how the input values and how we can get the output values. Previously we discussed about that CN. Same like that only this is also quantum gates controlled NOT. Previously, we discussed only that controlled NOT, CN. But here we have it as a controlled NOT. We can tell it as a CCN. So a gate which operates 3 qubits, it's called a controlled NOT. We can tell it as a CCN gate. So same conditions only, but here we have a 3 inputs. So the control line must have 2 input as a 1 and 1. So what are the control lines? A is the target, B is control 1, C is control 2. So B control have a value is 1 bit 1. Same like that, C control 2 also we can get 1. Then only the target value will be change the value. So invert that. So take that first input A, B, C. What are the output? A dash, B dash, and C dash. So 3 inputs we have. A is 0, B is 0, 0. So there is no any variation. We can remain the same outputs. That's it. Same like that. Second one remaining the same output. Third one 0. But we have 1 for B only, but not for C. You are not getting a in value for C. So condition is both B control 1 and C control 2 both are represent with value of 1. Then only it will invert the target output. So the third row also remain the same 0, 1, 0. And if you go for that fourth one, 0 is the target value. Input is 1 for B, 1 for C. So both control line having that value of 1. So what is our condition? Both are having that 1 means we will have to invert the value of target value. So target value is input is 0. So the output must be 1. So the output is 1, 1, 1. Same like that if you go for that fifth one, no changes because both B and C control lines are 0, 0. Next is also 0, 1 and uh, 7, 8, 6 also 0, 1. 7 you have that 1, 0. So B only having that control and C is having values 0. And if you go for the eighth value, both B and C having 1, 1. So we have that value of control value lines having that bit value of 1, 1. So automatically it will invert the value of target input value. So target input value is 1. So invert it and you can get the output. The output is 0. So this is the output we can get it from the 3 qubits. So quantum gates we are using operates on 3 qubits is called a controlled NOT CCN gate. So it will act like this. This is the input and this is the output. And if you go for universal quantum computer, the CCN gate has been shown to be a universal reversible logic gates. So that is the point. CCN gate has been shown to be a universal reversible logic gate as it can be used as a NAND gate. That can be used as a NAND gate. Same thing what we discussed in the previous one. The same thing only here. So A target, B control 1, C control 2. So A dash, output is A dash, B dash, C dash. So 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1. The same input values we are giving. What we discussed in the previous slide, same like that. The output is changed only in the fourth row. Next, if you go for fifth, sixth, seventh, it's having the same input values, but not at all having control B, control 1, C, control 2. So it's not at all having like that. So it won't affect it. But we come for that eighth one. Eighth one, we have it as a target value is 1, input is 1, input for B is 1, input for C is 1. So automatically when we calculate like this, the both are present 1, 1. So control 1 and control 2 is present 1, 1. So automatically we can invert that input value for the target A. So target A value is 1, that can be inverted as a 0. So we can tell that CCN gate has been shown the universal reversible logic gate. It can be used as a NAND gate also. So NAND gate also having the same property. So classical and quantum system, how it will be represented. Probabilistic states all of x, that is probability of x is must be greater than or equal to 0. and sum of x, probability of x equal to 1. This is the classical. And how you can, what are the things we can get the values means p000, p001, like that up to p probability of 111. The same time when we represent in quantum state is, that is all of x, alpha of x is belongs to c, that is the entire thing. Same thing represent as a sum of x, alpha of x the whole square equal to 1. So sum of x, alpha x of the whole square equal to 1. The same thing already discussed in the previous slides also. If you sum of the alpha x the whole square, sum of the value is always 1. The probability, the output is 1. So it can be represented in this form: alpha of 000, alpha of 001, alpha of 010 up to alpha of 111. So this is a direct notation. Notation can be represented like this. These are the basis vector. The first value is ket of 000, comma ket of 001, ket of 010 up to ket of 111. So we can rewrite that output, that is a ket of psi equal to sum of x, alpha of x, gate x. So we can write that equation like this. This is the classic and difference between classic system and quantum system states. See this one in direct Bra and Ket notation, how it will represent. Ket of ket psi always denotes the column vector. Example, alpha of 1, alpha of 2, it represent in the column based. So convention, if you take that state of 0 equal to 1 0, that is represent, show it in column format. Ket of 1 represent in the column format 0 1. Same like that, if you go for bra, there is a bracket only. Actually, I'll show in the next slide. Bracket can be taken like this. Bra of psi always denotes a row vector. So all the row vector we can represent the bra of psi. There is a always denotes row vector that is conjugate, that is a transpose of ket of psi. For example, we can get it in the row format. That is alpha of 1, alpha of 2, alpha of 3 up to alpha of d. So ket of psi is represented in the column format, rho of psi is represented in the row format. So this important notation we have to understand. That is a direct bra slash ket notation. See this, actually it is a bracket, can be splitted like this. So it will be denotes psi gate of phi, gate of psi. So the inner products of ket of pi and ket of psi. So this is the formula denotes like this. Product of, see these products, the inner product of ket of pi and ket of psi, it will represent like this. For this one we have an example, basic operations on qubits. Initialize the qubits in two states, ket of 0 or ket of 1. So we can use that unitary operations, that is u of, so formally that u of u equal to I. So we can conjugate that transpose, we can have that example. In this one, rotation by theta, how it will be represent, cos theta minus sin theta minus cos theta, like that. And the same thing, if you're not having that not bit flip means, how it will be represents, that is psi of x equal to x 0 1 1 0. How it will mapping will be represent, maps of ket of 0 is represent as a 1, ket of 1 is represent as a 0. And the phase flip z equal to 1 0 0 minus 1, it can map this. See the difference, the map is, it might represent that ket of 0 represent ket of 0 only, ket of 1 represent minus 1. If you go for phase flip, not bit flip is different. Understand that how we are assigning the values. If you go for phase flip means it will map the initial values. Ket of 0 is represent only the value is also ket of 0, and ket of 1 represent that -1. And the basic operation on qubits, it is a head-mud operation. See this, what is there. See this diagram, we have a x-axis and y-axis. That is, x-axis we have its ket of 0, and y-axis we have a ket of 1. At the same time, if the value is changed, there is a head-mud of state is changed now. Then state of change 0 is represented as h of ket of 0 and h ket of 1. The state is changed. We already told about that the atom will rotate in all the directions. The changes will be occur various states. It will be represented in various states. That means how we can make use of the unitary operator. See that h equal to 1 by root 2 into 1 1 1 minus 1. So the same, that is the equation we have already we discussed in that gate also. So the same thing we can represent in that form of what is the output of this h of ket 0 equal to, so 1 by root of 2 ket of 0 plus ket of 1. So what is the output? The output is 1 by root 2 plus 1 and plus 1. If this state is represented like this. When we go for h of ket 1, that is equal to 1 by root 2 ket of 1 minus ket of 1. So what is the output of this one? 1 by root 2, the state is plus 1 and minus 1. So this is the way we can get the output for head-mud equations. And the basic operations on qubits, probability, apply standard measurements, alpha into state, what is the ket of 0 state, plus beta into ket of 1. So we have a 2 states. And what is the output? What is the probability we can get? We can get 0. That means with probability alpha the whole square. Probability, that is the values we got 1 with the probability of beta the whole square. So this is the way we can represent the basic operations on qubits. And operations on n qubit states. See this, sum of alpha x, gate of x, it will give the values. Unitary operations u of sum of x, alpha x of gate x, that is ket of x. So that is the output. So what is the output for the previous input? For you are getting that 3 inputs we are having 0 0 0 like that. So that means what is the output? So output is with probability of alpha of 0 0 0 the whole square. Same like that, when you go for 0 0 1 with probability, we can get the value of alpha of 0 0 1 the whole square up to we have all the other values, and the last one is 1 1 1 is the input with the probability of alpha of 1 1 1 the whole square. So this is the operations on n qubit states. Same operations we can implement in entanglement. So previously we discussed about that what is the states of 1 qubit, 2 qubits, n qubits. That is the first one. Already we principles we discussed about that. These things already we discussed. What are the principles we discussed in the previous session? Hello, it's audible. Hello.
Yes, sir. You are audible, sir.
Yes. So superposition we already discussed in the principles. So whatever we discussed, that is the represents of the superposition above for 1 bits and 2 qubits and n qubit states. Next we go for entanglement, how it represent in the mathematical calculations. Suppose that 2 qubits are in states like this. There is alpha of ket of 0 plus beta of 1. So what is the output of this one? That is alpha dash of state is 0 plus beta dash of state is 1. That is ket of 1. So how we can get that entanglement? See this, the state of combined system, their tensor products, see this, alpha into ket of 0 plus beta into ket of 1 into, that is multiplication of alpha dash of ket of 0 plus beta dash of ket of 1. So we take two input values. One is alpha of ket of 0 plus beta of ket of 1, that combination multiplied with the alpha dash of ket of 0 plus beta dash of ket of 1. So if you multiply this state, that is a tensor product we are having, that what is the output? That is alpha dash ket of 0 0 plus alpha beta dash ket of 0 1 plus. So see that you can easily understand that first you multiply that alpha ket of 0 with the another term of alpha dash 0. So we can get the output is alpha ket of 0 in product, we can get that alpha dash of ket of 0. Take the second term, alpha ket of 0, multiply with the product with the beta dash of 1. So that's why we have that alpha beta dash of ket of 0 1. Same like that, take the next term, beta of ket of 1, product with alpha dash of 0. That's why we have a beta alpha dash of ket 1 0 plus last product beta ket of 1, product with beta dash of 1. We can have that beta dash of ket 1 1. So like that we can get the output. So entanglement, we already told that one state will combine with the opposite state. There is a two states will be there, that each and every states have their interlink of that one. It will be depends like that. Same like that you can do for some more operations like that. We go for next, structure among subsystems, qubits, and in that qubits we can use that u, that is unitary operators, and we have vectors, and we have w's. If you make, and we can use that and gates, that for measurements. These all are the unitary operations, u v w like that, and the last we have it as measurements, and finally we can get the output. So same like that, that is a structure among subsystems. That is a 1 2 3 4 like that qubits. We have a 1 2 3 4 qubits. It can represent by the support of unitary operations and the measurements, we can get the output. See this one, quantum circuits. We can give that input as a qubits. That is state is 0, ket of 0, ket of 1, ket of 1, ket of 0, ket of 1, ket of 0. We can give the inputs. So in between we have as a unitary operators, and we have a gates. After finally we can get the result 1 0 1 0 1 1 like that. So this is the computation is feasible if circuit size scales polynomially. So this is the example shows that quantum circuits. Same thing we already discussed in the previous session also. So we can give the give the inputs, and how we are getting that outputs. The output is represent is the alpha 0 dash plus alpha 1 dash, that is equal to g11 g12 g21 g22, that matrix product with alpha 0 and alpha 1. So if you make a product of this matrix, we can get the output of alpha of 0 dash and alpha of 1 dash. And see that example, 1 qubit gates. So previously what is that same thing, g is equal to g11 g12 g21 g22, and if you transform that g of t, that is g11 g21 and g12 and g22, the transfer swipe. Already I told in that gate also, swipe gate like that. And what is the output? We can get it for g plus, there is a g11 asterisk, g21 asterisk, and g12 and g22 asterisk. So if you make a product of these two, g and g plus, so what is the output? So finally if you make that product, of these two matrix, we can finally we can get that output as a I. So this is the way one qubit gates can be represented. And we can have some of the examples of representation of uh, transformations, polymetrics, and Hedmerd. So generally we know about that alpha of 0, alpha of 1, alpha of 2, alpha of 3. That all are I equal to 1, 0, 0, 1, x is equal to 0, 1, 1, 0. This all we can get it as a polymetrics. And H represent means we know very well about that Hedmerd matrix. So what is the output for this one? We can get it in the right hand side. And take one more example for this tensor product and outer products. So we have a two inputs, that is a 0 0 ket of 0 0, that is equal to ket of 0 product cross product of ket of 0. That means we can get 1 0 and of 1 0, that is equal to, we can represent that gate in column based, that is 1 0 0 0. If you same thing, if we go for products of 2, what is that? Ket of 0 0 and bra of 0 0. So ket of 0 0 represent that in column based, bra of 0 0 is represent in that row based. So ket of 0 0, we have 1 0 0 in column based, and bra of 0 0 represent in the row 1 0 0. So if you make that product of these two, ket of 0 0 and the bra of 0 0, means we can get the output is matrix form. We have it as 1 0 0 0 0 0 0 0 0 0 0 0 0 0, and finally we can get 0 0 0. Like that we can get the output. This is the tensor products and outer products. And again we go for that cn not a 2 qubit gate. There is control input and a target input. We already discussed the same thing with example C naught. Mainly important point is we have two inputs. One is control input and target output. The control qubit is transferred to the output as is. The target qubit unaltered if the control qubit is 0. It will be flipped if the control qubit is 1. So the same thing we have discussed with the example also. If the controlled bit we have as a qubit is 1, means it will be invert the input value of target. That is the thing. And same we can represent in that C naught. So vector of C naught equal to ket of psi in, there is an R set of ket, sorry, ket of pi. If you have a product of these two, ket of psi into ket of pi. So what is the output? There is a W of C naught equal to G C naught gate of V C naught. So what is the G C naught output? 1 0 0 0 1 0 0 0 0 0 1 0 1 0, like that. And we have a two input qubits of 2 qubit gates. What is the first input is ket of psi, that is equal to alpha of 0 ket of 0 plus alpha 1 ket of 1. What is this other input? Ket of pi equal to beta 0 of ket of 0 plus beta 1 of ket of 1. There is a two inputs we have, one is ket of psi and ket of pi. If you have a product of these two, cross product of these two, there is V C naught, that is equal to ket of psi product of that set of pi. So what is that? That is the input of this one is alpha 0 and alpha 1 product with beta 0 of beta 1. So this output we can represent in this way: alpha 0 beta 0, alpha 0 beta 1, alpha 1 beta 0, alpha 1 beta 1. This is the output we can get it from these two inputs. And two qubit gates, we have a C naught, G of C naught, that is ket of 0 0 and bra of 0 0 plus get of 0 1, bra of 0 1 plus get of 1 0, bra of 1 0 1 1 plus get of 1 1 and into bra of 1 0. If you make these products, And if you add all the values, we can get the output g of c naught, that is we can get output like this: 1 0 0 0 1 0 0 and 0 0 1, and we have a 0 0 1 0. So like that we can get the output for 2 qubit gates. And see this one, 2 qubit gates, the product of this, we already previously we know that value of g c naught and v c naught. Now we can find that product multiplication, that is the product of g c naught with the v c naught. That is the how we can get it represent g c naught of ket of v c naught. So the output of w c naught equal to g c naught, already we know the value 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0 product with v c naught. V c naught, previous slides we discussed that, and alpha 0 beta 0 alpha 0 beta 1 alpha 1 beta 0 alpha 1 beta 1. If you make this product, we have that output of alpha 1 beta 0 alpha 0 of beta 1 alpha 1 beta 1 alpha 1 beta 0. See this output. Output can be represented in the form like this: w of c naught, that is equal to alpha of 0 beta of 0 ket of 0 0 plus alpha 0 beta 1 ket of 0 1 plus alpha 1 beta 1 ket of 1 0 plus alpha 1 beta 1 ket of 1 1. So this is the representation of value. We can get the output of w c naught. The same we can modify like this also: v c naught, that is equal to alpha of 0 ket of 0 beta of 0 ket of 0. We can split it plus beta 1 of ket of 1. The product of, see that product we can rewrite like this: alpha 0 ket of 0 we can take out, the inner bracket we have it as a beta of 0 ket of 0 plus beta 1 of 1. Same like that, if you take the alpha 1 of ket of 1, if you take out of this alpha 1 of ket of 1, bet beta 1 ket of 0 plus beta 0 ket of 1. So we can rewrite the previous equation. The output we can rewrite like this: we can one term, the alpha of 0 of ket of 0 and alpha 1 of 1 we can take out. So final comment on the c naught gate. So c naught preserves the control qubits, and the first and second components of the input vector are replicated in output vector. That is the thing. What is the use of the c naught? Preserves the control qubit and flips the target qubit. You already see the example how it flips based on the control and flips the target qubit. And what is the output of this one? W c naught, that is equal to alpha of naught set ket of 0, that we already discussed that. So this is the final comments on c naught gate. So c naught gate is reversible. The control qubit is replicated as the output, and knowing it can be reconstruct the target input qubit. So this is the importance of c naught gate. And the example of 1 qubit gate applied to 2 qubit system. That is 1 qubit gate can be applied to 2 qubit system. So we'll see what is that. See this mapping of this one. So this is the way of having that resulting of 4 cross 4 matrix is I, then there is a product you can make with u. So what is the output? So before that we can have a states, 2 states. I told that one is 1 qubit gate, another one is 2 qubit gate. So first one, take that 1 qubit is ket of 0 ket of 0, that is represent is ket of 0 u of ket of 0 ket of 0 of 1 ket of 1, like that you can represent. So if you have a matrix and what is the another output is, we have that ket of 0 u of 1 ket of 1 and ket of 0, and the third one ket of 1 u of ket of 0 and ket of 1 ket of 1, and the last one ket of 1 u of ket of 1. Like that it will, values will be changed, maps basic states. Once we have make the products of I product with u value, we already know that u of 0 0, u of 0 1 and u of 1 0 u of 1 1. That is the value of u. And if you have a 2 qubits, what is the previously we discussed the 2 qubits output 1 0 0 0 0 1 0 0 like that. So if you make the product between u value and I value, they make that 4 cross 4 matrix like this. That is u of 0 0 u 0 1 0 0 u of 1 0 u 1 1 0 0. And the same time third row 0 0 u of 0 0 u 0 1 and the fourth one 0 0 u of 1 0 u of 1 1. If you apply, if you have a time, you just work out on that, you can get the result of 4 cross 4 matrix between u and I. And the controlled u gates, so already we discussed about that controlled u gates. Same like that, if you have a controlled u gates means we already know that if you have a controlled value is 1, the output must be flipped or inverted. Same if you apply the same thing control u gates for the above product of I product with u. With controlled u gate means the output will be vary. So what is the control u gate output is 1 0 0 0 0 1 0 0 and 0 0 u 0 0 u 0 1 and 0 0 u 1 0 u 1 1. You can find the difference between these two outputs. The first row and second row, it's affected the values, so you can get 1 0 0 0 only. So that is the controlled u gates can use this condition. So already I told about that. What is the control u gates? It can represent with two inputs. One is the controlled input, another is target output. So controlled input have a 1 means it will be flips the value of target output. And the controlled not c not, see that a get of a gives get of a, here get of b, here only we have a operation of that and a product with b. See this, how we can get the values. First one, there is no any change control. So get of 0 plus get of 1, you can get that value get of 0 and minus 1. Same if you go for this one, get of 0 minus get of 1. So here only we have that changes and we can get the value. That is control value cannot change, the target value only change. The target value already changed minus 1, and here control value cannot change, you can represent the same get of 0 minus get of 1. That same thing we can represent in that head mode. I already told that head mode and control c naught will be the same. And the multiplication problem, okay, I will complete it within 2-3 minutes. It's okay following. Hello.
Yes, sir, we can hear you.
Yeah, yes. Multiplication problem, this is one very important one. I'll complete I'll close with this example. See this, two n bit numbers, we have a 0 0 1 0 1 and 1 1 1. If you go for this product of these two values, we can get the output 1 0 0 1 1. So yeah, if you go for this algorithm, the speed we can have that grade school algorithm takes, what are the steps we can taken for this one. Currently we go for classical algorithm also, we can get the same result. Both quantum computing based product or classical based also getting the same result. Best is currently known as quantum method. But this is okay, previous slide multiplication problem. But if you go for factoring problem, this is the very important. I think first session I told I will tell with examples like that. This is a factoring problem. It's one of the important thing. You can make the difference between that classical computation as well as the quantum computation. Take that input bit is number same value, previous slide input we know that 101 and 111, output is 10011. See this input number is 10011, the output of the product is between, we can go for factoring problem for this 10111. The trial division cost is 2 to the power of n by 2, the currently known as classical algorithm. See this cast O of 2 of n power 1 by 3 log of 2 by n by 3 n. So it is very tough to go with classical system when we have a input is 100011. We want to find out what the combinations we can get it for this one, for getting this number. For example, I'll tell one thing. 6. Suppose we have a two inputs. We have a input 2 3. If you give input 2 and 3, if we are asking that output is product of these two values, 2 into 3. So we can get that output. We know that product of 2 and 3 is 6. We can give the value of 6. That means classical computing also give the 6, quantum computing also gives 6. The output is same, we can understand that. But at the same time, if you go for factoring problem, 6, what are the combination is there for getting the product of 6? So we can't tell only that 2 and 3. So we can get 1 into 6. Like that, we can have some more options. If you 6 is a small integer number, we go for 1024 or any lakhs numbers. If you have a lakhs number of values, integer values, if you go for what are the combinations is there to get the output, that is the question. Previous slide shows that 100 into 120, we can get what is the output. So 1200, suppose we are having the 1200 output. But what I'm telling for there's a second one, factoring problem. If you have a 1200, what are the combinations there for getting the output of 1200? So this combination, if you go through classical computing, is not at all easy. Take long time to get the combination. But if you go for classical computing is getting long time, cannot get it. But at the same time, if you go for quantum computing, it will be easily find out that output of this. What are the combination is there for getting the output of 1024? If that is a reversible product. So from there, what we are getting that if when you go for cryptography in encryption, decryption, RSA algorithm, so this combination work out on that. Suppose encryption key, you can easily find out that we can destroy that algorithm or RSA by using quantum computing. This is an important information. So if you're using factoring problem, you can do like that. And some more algorithms is there. I already told about that. There is Grover's search algorithm. It is finding the names in the database that is randomly entered. That will be easily find out by using that Grover's search algorithm. So that will be averages n by 2 search is required. So it will be very fast in quantum computing representation. That is square root of n, O of square root of n. That is very fastly it will find out that value. And that's problem. So if you have a 4 possibility outputs like this, and goal of determining of f of 0 product with the f of 1, and reversible black for f, and quantum algorithm for Dutch. So we have a lot of algorithms there. Quantum algorithm 1, and quantum algorithm 2, and quantum algorithm 3, how it will be represents. So we have algorithms also. We go detailing about that algorithms. It will take time, so I'll try to conclude now itself that quantum algorithm, and what makes quantum algorithm potentially faster. So quantum parallelism, and the dimension of quantum Hilbert space, and entanglement capability. We already discussed about this and all. And quantum algorithm search like this, all will be supported. This algorithm and principles and structure all will be support for quantum computing. So quantum computing make wonder, and it represents to calculate large number of complex mathematical problems within a minute or within a seconds. Thank you. If you have any query, you can ask. I think you all understand that. So,
Yes,
some more mathematical terms.
participants, any
Board
questions
means it's
for
very easy to
sir?
explain that each and every step. Ma'am,
Yes, sir. Yes, sir. So thank you, sir. Thank you so much. From behalf of the organizing team, I sincerely thank you for sharing your valuable knowledge and expertise during this session. Uh, your inputs were really enriching, and it was understanding, sir. And It was really great. It was success for this session. And sir, hello.
Okay, thank you, ma'am. Yeah,
Yes, sir.
yes, ma'am. Continue.
Thank you so much, sir. Thank you so much. Also,
Thank you, ma'am. Thank you for giving.
yes, sir. Thank you
Yeah,
for
tell, ma'am.
giving your valuable time, sir, to us.
Yes, ma'am. Thank you, ma'am. Thank you, participants. So if you have any doubt, you can get my mail ID and you can ask any questions. Thank
Yeah.
you.
Thank you, sir. Thank you so much.
Thank you, ma'am.
Also, I would express a sincere gratitude to all the participants for your active involvement and participation. Thank you all once again for making this FDP session successful. I will be looking forward for your continuous participation in the future sessions also. Thank you, everyone.
Thank you.
Thank you,
Participants, I
ma'am.
will. Yes, sir. Thank you so much. Participants, I'll be sharing you the feedback link. I request all the participants to attend all the session, as all the sessions are being recorded, as well as your attendance is being recorded. So 80% of the attendance is mandatory to get certificate. And also I'll be sharing the feedback form on the group. Please kindly fill that form. Thank you, everyone, and good night. Tomorrow we will be seeing another session with another expert faculty. I'll be sharing the
Oh,
link on the group, on the WhatsApp group.
okay, thank you.
Okay, thank you, sir. Thank you, everyone.